All right, so if we're going to study rates of change, we're just putting derivatives to use in the real world. Okay. For example, I have a brother-in-law that is an engineer. He's graduated from mines, and he had a job where they did car accident analysis.
Any remaining sophomores that need retakes or need a student ID, please report to the gym at this time.
So he was using a lot of position analysis, a lot of velocity analysis. All that's calculus-based, rates of change, right? So remember, let's say, I think I gave you this right once. I'm going to drive from Parachute to D-Town because they're so gangster. Right? That's how the freeway looks, I think. Okay. Let's say you're at Parachute, it was 0 and 0, right? How long does it take you to get to Denver?
Right now, probably like 6 hours.
Why?
You know, construction and snow.
Okay, it should be 3 hours
3 hours?
and 180 miles.
No? It's 201.
It's 201, takes you 3.5 hours.
To where in Denver?
It says 201 on the mile marker sign.
Yeah, it definitely says
I
201.
promise.
On the sign post?
Yeah.
Oh, on the sign. Okay. Well, we'll just go with it. Okay, can you calculate the average rate of change?
You totally wanted an invisible number back there, didn't you?
Yeah.
No, but that was not in my mind. Okay, what's the average rate of change here?
60 miles every 1 hour.
Right, slope formula, right?
Oh,
60 miles per hour.
180.
Okay.
I'm like, how did you get 60 out of that?
That's a rate of change. We've already studied this kind of thing, right?
Right.
Like I said, we've already started it. Can you calculate the instantaneous rate of change at any one spot?
Yeah, well, that's 120.
Did I give you enough data?
No.
Okay, not enough data. Okay. Okay, I'm hearing slope of tangent line and stuff like that. That's perfect. It's the instantaneous velocity, right? In this case. That would be the contextual interpretation of instantaneous rate of change in this instance. Can you give me an example of instantaneous rate of change if you're driving from Parachute to Denver? Yeah, just give me an example. What?
How fast you're going past the exit?
Yeah, so let's see, you're going past Vale exit. That's how fast you're going at that moment. The key there would be at that moment. Can anybody give me an example of a person that takes your instantaneous rate of change? Popos, the police officers. Yeah. So the police officers, when they radar gun you, that's an instantaneous rate of change. Right. So all they have to do is catch you at any one moment going over the speed limit to pull you over. Right? And hopefully you actually pull over.
How would you classify the air enforcement? Like when they, because they measure you from like point A to point B and
That's
average
good.
rate. Is that instant rate of change or? That's a secant line.
Okay, Montana is an excellent question. And that is? How would we classify the air-based?
Huh?
Do you know what that is? Like, so it's
So, go
law
ahead.
enforcement enforced by air. They have like a white line on the or in the freeway, like at point A, and then another one like 200 yards down, and then they have like a chart, and if you pass those lines in X amount of time, that means you're going so fast.
Huh.
Right.
Wow, that was.
So how can they use that?
They're like
This is,
it was
okay,
air
so
or
Which one of these two is it?
It's a
That
second
average.
rate.
This is average rate of change. How can they justify using that to give you a ticket?
Because it's within a certain, like, it's
Yeah.
not between celebrating.
Exactly. If your average rate of change is, let's say the speed limit, limit, good word, is 75, right? If your average rate of change is 85,
Speed.
does that tell you that the instantaneous at any one moment is at least 85?
Yeah.
Yeah, it does. So this implies, that equals 85 at some moment.
I did that backwards.
You know why they can do that?
Because they're like cops.
Because they're cops and they can do anything? No.
Plus, that's also Johnny can do cards.
There's this thing called the mean police officer, value theorem. That's section 4.3 in our book. Thanks, Monte.
Wow.
You've already learned some applications of derivatives.
So I could do. Oh boy.
Yeah, that's called the mean value theorem. If there's a continuous function that's differentiable and the average rate of change is 85, there was guaranteed an instantaneous rate of change of 85. There you go. Okay. You just haven't formalized it in calculus talk.
Yeah.
You've been doing slope since you were in 7th grade. You just haven't put it in calculus talk. See why I think calculus is easier than pre-calc?
Yeah.
All right, let's take a look at a problem. A truck.
Oh yeah. I love trucks.
I like trucks. Enters and the off-ramp of a highway
I don't know. I haven't had it.
at equals 0. Its position after t seconds is
No, because I'm like writing several times. It's amazing. Highlight.
I should just rewrite that. Okay. All right, so we've got our information.
What did that mean? Oh, okay. I'm so used to seeing variables in the problem. I thought 4 was part of the equation. Whoa.
So is that 0.3?
Yeah.
Okay.
Okay, so I've just made a statement. There's no question here yet.
Long statement.
Yeah. Could we calculate average rate of change? Yeah. Yeah, you could. Right? So S of 5 minus S of 0. So something you already should be able to do. Right? Average rate of change. The questions we usually get from these are something like, how fast is the truck traveling when it enters the off-ramp?
I don't know.
Yes, you do actually.
Just plug in 0, right? did we do?
Yeah, yeah.
Does this give us speed?
Yeah.
Does that function give us speed?
No.
No, it gives us position.
Oh,
So if you plug 0 in, you get the position of the truck,
0.
which is
You
0.
go to the
87.5 miles per hour.
Okay. How'd you calculate that?
I plugged 5 in.
Why?
Okay, first of all, let's determine how fast is the truck traveling when it enters the off-ramp. When does it enter the off-ramp?
At 0.
T equals 0.
So it'd be 0.
Okay,
That.
So what
how do I calculate? And this is an instantaneous rate of change question. How do I calculate instantaneous rate of change?
You, normally if you pick a point that's on that tangent line, but we don't got that tangent line.
No, how do you figure it out?
You have
Do you do like point zero zero one?
derivative equation?
You guys are making this way too
So do you
complicated.
use the average rate of change?
Thank you for using that word. Say it again. Derivative is instantaneous rate of change,
Oh.
right?
Yeah.
So what's the derivative of S?
Oh, this would be,
25
Oh.
minus
wait, so that's.
0.9 t squared, right?
Yeah. Plug in 0.
This is our speed or velocity function. Instantaneous, the derivative. So yeah, now plug in 0.
So there's 25. Other 25
Yeah, 25.
miles per hour.
Second, meters per second. Okay, M is meters in this case. Okay. So
1 meter per second.
what relationship did we just learn about?
Average rate of change and derivative.
If you are a golf boy, please come to the gym for your pictures. The golf
Velocity.
boys, please come to the gym.
Is the derivative of position. You will know that relationship. Because we're going to work at both directions. We're going to add acceleration in there too.
That's good.
All right, so if you have a position function and you're asked about velocity at some moment, that is a derivative question. Right? Does that make sense?
So going back to that, are you live streaming what's
Yes.
on the whiteboard?
He is. He does it every day.
So if we go back to the first example between parachute and Edward, if we take the point, like say the cutoff or whatever, and we find the slope, that's how fast we're going to.
At that moment. If you have the graph or the function. We didn't, but yeah.
Yeah, okay.
Okay. Here's another question we can ask. Is the truck speeding up or slowing down?
When? As it enters the off-ramp.
You can enter it from the highway.
So it'd be slowing down as it enters the off-ramp.
Maybe.
I would be speeding.
I hope not.
That's a real question.
So you're thinking contextually, we need to verify that mathematically.
Darn.
So is it because it's the.
How do I calculate? Okay, this is another way of asking about
Oh, off-ramp.
acceleration, right?
Alright.
So would you have to find the slope?
Acceleration is the rate of change of velocity.
Yeah.
So how do I use my velocity function to find acceleration? Huh?
The average rate?
Nope.
You compare velocity at point 0 to point 5.
Nope.
Or 5.
You could do that.
You have to take the derivative of that function.
Yeah, we could do another derivative.
Oh, wait, what?
Yes.
The derivative of the derivative?
Uh-huh, yeah.
You derive the derivative.
Why?
Because acceleration is a derivative of velocity. Acceleration is the rate of change of velocity, right? So the second derivative of t, of s at t, is negative 1.8 t.
It's called double prime.
So what's, is it just, what is double?
Well, since
Yeah, this is double prime,
Ooh.
higher derivative.
Will we ever get that?
Zero.
So this is one way to tackle the problem.
Right.
Hinges on fire.
It was 2
So then what you take the velocity and subtract what you get from the derivative
Okay.
of this?
All of the time values are positive, correct?
Yes.
So if I plug a positive in here,
It's gonna be negative.
negative, so we are
Decreasing down.
slowing down. Yeah. So the truck is slowing down.
Unless you're some maniac and you speed up on the off ramp to.
Because for the second derivative lessons.
Well, can you identify that speeding down the way the exponents are?
Speeding down?
What?
It's slowing down. Because like in the original equation, 25t minus 23t cubed, you can tell that the negative.
cubed.
Yeah, so you could also say that this is you can say this function is decreasing
Yeah.
because it's negative t squared. So what is the graph going to look like? Right, so we are decelerating. You could say that too, using the graph. Okay, so velocity, so we have our relationship. We have position, and we have velocity, and we have acceleration, right? This is usually going to be called S of t. The velocity is the derivative, sometimes noted v of t. Man, he's loud. The acceleration is s double prime at t, which is also v prime at t, right? We will note that a of t. Okay.
Wait, so why is it double prime?
Two derivatives. Right. First derivative, second derivative. So what's the third derivative? Triple prime. What's the fourth derivative? No, it's s to the fourth.
Oh.
But you don't know that. Don't worry about
Yeah.
it. Okay, I tricked you. Are we good there? Done writing?
No.
Got one more to do and then we'll be done.
But then you have more than one page.
I'll show you how to get more room.
Okay.
Whoa.
What?
Love it. Good. Yeah.
What's that?
Scroll buttons. Okay.
What's that?
S double prime at t
After the
equals v prime at t equals a at t.
A, okay.
Acceleration, a of t.
I thought it was a 9.
I just
Like, it
can't
looks
stop
like a
showing
weird
that
cross
picture.
of a 9 and
That was you, straight up.
What?
it looks like a weird cross of a 9 and a P, so.
It's an a. Okay.
So I guess, yeah.
Circle.
Ow.
What's the area of a circle?
Pi squared.
Okay. Can you calculate dA dr at r equals 2?
Yes.
Yeah.
Okay. What is it?
Does that say DA and DNR?
dA dr.
2R.
So what is dA dr?
It's 2R.
It's 2 pi r.
It's 2 pi r.
Oh, you can't get rid of the pi?
Only if it's a loner. It is not a loner. It's hanging out with his friends. Okay.
And then you plug in 2.
Now plug into 4 pi.
So why do we need another slope of the circle?
What? Not slope of the circle. Rate of change of the radius of the circle.
Wait.
Wait, why would
If
that
the
be a
circle's
thing?
growing or shrinking, which happens in real life, right? Oil slicks, balloons, they grow and shrink. We've talked about rate of change of circle radiuses, area. We'll get all that stuff. But for now, just be able to take a formula, calculate a derivative, and plug and chug. Okay. It's just a contextual geometric shape. All right.
Shame on you.
Okay. 11. I'm going to take a little bit off of this. So we've got rates of change, contextual problems, and you've got some AP review, and then power rule and product and quotient rule.
Was that 7 and 8?
Does that say 9A? Yes.
9A and B.
And then 50 for 3 reduce 7 and 8, yeah. Or is that a 3?
That's pretty.
3 and 8.
Is that
It's
like
a
my
good goal.
You do good all lesson almost with like handwriting, but as soon as it gets to like writing the homeworks down, notoriously it just it's the whole thing.
I'll fix it.
It was just an observation.
That's something I need to know.
Do you have the same homework for A
Like,
and
there's
B?
always a question.
No.